And this brings us to plate tectonics. Plate tectonics is the movement of plates and the forces acting upon those plates. Now, this includes the forces that create the plates, the forces that move the plates, and those that may destroy them, or at least drag them down to the core mantle boundary, where we more or less lose track of their shape and chemistry. This theory of plate tectonics explains the distribution of volcanoes, earthquakes, mountain chains, rock assemblages, and seafloor structures. Things that we've known about for a long time it couldn't necessarily explain. And it's driven by the mantle convection system. And we're going to be talking about that more over the next few lectures here. Okay, so this starts out when I was a kid. I had a toy truck, looked kind of like this. Probably belonged to my father or my grandfather before me, explaining the outdated cab. So I was looking at this truck one day when I was probably 4 or 5 years old, and I noticed that the continents could be moved together like pieces of a puzzle. And so I asked my parents, hey, why is it looks like these things would fit together like a puzzle? And they said, be quiet. How about if we go to the zoo and you could talk to a camel? And I thought, okay, I'll go to the zoo and I'll talk to a camel. But I still want to know about these things here that look like they fit together in a puzzle. And I received no answer. About 60 years earlier, Alfred Wegener developed a theory of continental Verschiebung. This was developed in a lecture in 1912. And unfortunately for him, he was forced into World War I. He was quickly wounded twice in Belgium. And because he was far too injured to continue fighting, they gave him a job as a meteorologist for the German army. So he spent the rest of the war traveling between weather stations throughout both continental Europe and Eastern Europe, principally. He went on in 1915 to publish a paper called The Origin of the Continents and Oceans. So this is a guy who is a meteorologist by trade. He is in battle, traveling from weather station to weather station, and writing a book about the origin of the continents and the oceans. Pretty much of a go-getter. He was also part of the first expedition to spend the winter in Greenland on the ice sheet in 1912. He ended up going back to Greenland a number of times. He was working on his ideas about what would ultimately become known as the jet stream. He died on his fourth expedition in 1930. He was traveling with one other member of the team to resupply another group that was isolated, and most likely he died of a heart attack. He was in his 50s, a heavy smoker, and it's a lot of work to move things by sled over uneven ice, so that's probably what ultimately killed him. He was buried, and it's believed now that he is covered by 100 meters of snow and ice since his burial, since his body was briefly recovered and then reinterred. Unfortunately, they buried his diary with him, so we don't have the record of his last expedition. Well, we do, but it's buried under 100 meters of snow and ice somewhere in Greenland. So what was he doing? What was he talking about? Well, he noticed early on, about 100 years ago, a little more than 100 years ago, that the continents could be fit together like a jigsaw puzzle. So South America and Africa fit together. North America fits between Africa and South America. Europe can slide in north of Africa, east of North America. Antarctica and India are located down here. In addition to these continents fitting together like puzzle pieces, we can also match up some pieces of these puzzles using rocks. Rocks that we see on one continent appear to be very, very similar to rocks that we might see on another continent. This happens over and over again in different locations. Different rocks appear on both sides of a large ocean. Now, if we throw in the continental shelf, the shallow areas that were exposed during the height of the last glacial period, we get an even better fit. So the continents fit pretty well from their outline as we see from satellite images today. But if you go down 100 meters or so, the fit is even better. So he noted that the continents fit together like a puzzle. He noted that there was a similarity of rock assemblages and rock ages across the oceans. Now, the rock ages were only going to be determined by fossil assemblages at this time. We didn't have the chemical means that we have today to determine rock ages. So here we have an example, one of the more famous examples of this theory, the presence of mesosaurs on both sides of the South Atlantic. So we have mesosaurs here in Patagonia, and we also have mesosaurs over here in South Africa, in the Namib. And because these are freshwater reptiles, they didn't swim across the Atlantic to occupy both of these places. It's very strong evidence that this land was connected to this land when they were both freshwater environments. So we have this fossil evidence, again, throughout the world, not just this one location, this one example. There are lots of examples. We can see that the seafloor is spreading. We can now observe geological activity at mid-ocean ridges. We didn't know about these until fairly recently, but now that we do know about them, and now that we have the technology to watch them, we can keep much closer tabs on what's going on there. These mid-ocean ridges ultimately result in the formation of new crust. So all along this mid-Atlantic ridge, we're creating new crust. This new crust is going to spread out to the east and to the west from this ridge, essentially making the Atlantic Ocean bigger and the Pacific Ocean smaller. Now, in some locations, like Iceland, we can see the rift appear above sea level. When we look back in time, over the last 300 million years, we can piece the continents together, as you see here, with only some missing bits and pieces, only a few missing bits and pieces. These bits and pieces may be found at some point in the future. Some of them already have been found since this figure was made. And again, this is a fairly simple cartoon, so don't take it too critically seriously. So what you'll see here, trending from 300 million years ago to about 1 million years ago, is the continents breaking up, spreading apart. By 50 million years ago in the Eocene, the Atlantic Ocean is forming. The Pacific Ocean is getting smaller. We're crunching down on that to create the Atlantic. And by about 1 million years ago, during the height of the Pleistocene glacial period, we can see the continents are pretty much in the same position they are today. The difference being that a lot of this shallow ocean today was exposed when the ice sheets were at their maximum. So we put the maximum amount of fresh water on top of the continents at the high latitudes. We lower sea level by about 100 meters. We expose this continental shelf. Which brings us back to earthquakes. Now, what is an earthquake? An earthquake is the sudden release of stored energy as a result of rapid movement between two blocks of rock. We can see that depicted here. A couple different features of earthquakes. The focus is where the actual slippage occurs. That's at some depth below the surface, almost always at some depth. The epicenter, that's on top of the center. So on top of the focus is the epicenter. The surface of movement, the surface on which the movement occurs, is known as a fault. And what we see at the point of an earthquake is the emission of energy. This emission of energy is going to be depicted by waves, first the P waves and then the S waves. Those wave fronts are going to move out from this focus in every direction until they reach the surface, and then the P waves and the S waves are truncated. Surface waves, of course, can travel along the surface here. So these earthquakes are going to occur where rocks are being stressed. The stress builds until the rock reaches its breaking point, essentially. And once the breaking point is reached, the rock breaks. When this rock breaks, it moves. One bit of rock moves relative to another bit of rock, and that displacement is the energy, the energetic impetus that generates those seismic waves. These seismic waves are ground vibrations caused by these rocks slipping along opposite sides of the fault. Why does this happen? We're going to go with the elastic rebound theory. This is a theory in which stresses will build over a period of time. The rock ruptures when it reaches its breaking point, its point of rupture, and the stresses are relieved. Subsequently, the stresses will start building again. Eventually, we're going to have another break and another elastic rebound, and this continues on and on. The result is a fault rupture, which we can see here. The rock is going to break, it's going to slip along this fault in a fault rupture. And we talk about the meaning or definition of epicenter. It's the point above the focus, the point on the Earth's surface above the focus, which is the point within the Earth where the slippage occurs. Now, we've looked at something like this before. The different types of waves are depicted here. P waves, or primary waves, can be thought of as compressional waves, like taking a slinky and pushing it in this direction. You're going to add a wave to this spring, this slinky. This wave is going to travel in this direction until it reaches the end, and then it's going to travel back. Now, the other common type of wave is known as an S wave, or secondary wave. This is a wave that's more akin to what we see in the natural world, in environments like a lake or a river or the ocean, where an inflection is induced upon a spring here, and this causes the spring to wave. So it's going to rise and fall. This inflection that we induce upon the wave is going to travel the length of this spring, and again, it would return if given the chance. Then we have surface waves where we actually see vertical displacement of the Earth's surface during strong earthquakes. We saw some video of that on the previous section. Now we're going to use that energy emitted by earthquakes to produce a three-dimensional model of what's going on within the Earth. In this example, we're looking at a tomographic image of the mantle based on S waves and P waves. And we're looking at this particular transect across North America, across the United States, and northwesternmost Mexico. When we do this and we look down into the Earth, what we see are the ghostly remains of the Farallon plate. This is the plate that is being subducted under North America. We can see starting 80 million years ago, the Farallon plate was being subsumed by the North American plate here. At about 40 million years, it started to become detached, and we can see that there's probably some distortion introduced into the plate by this time. So the plate's getting deeper into the Earth where it's hotter and pressures are higher. This material is more susceptible to deformation without rupture. And we see by about 20 million years ago, this plate has been detached. And in the modern world, we don't see evidence for this plate at the surface in this region. So this is the consumption of the Farallon plate that we're observing here. Now, in order to talk about earthquakes, we need to talk about how strong they are. In talking about how strong an earthquake is, we're really talking about the displacement introduced by P waves and by S waves, most notably. So this led to the development in the late 20s and early 30s of the Richter magnitude scale. This is the scale we most commonly refer to earthquakes by. When we talk about a 9.0 versus an 8.0 versus a 7.3, we're usually talking about the Richter scale. And we can see, just for some examples here, some major earthquakes. The Chilean earthquake of 1960 is still believed to be the strongest earthquake recorded. The Alaskan earthquake, not quite as strong, but still substantial. And then getting back in time, we see lots of other examples of large earthquakes on this side of the scale. Some of the more memorable explosive actions that have occurred, some induced by people and some by nature. So when we look at the Richter scale, one thing to consider, perhaps the most important thing, is this is not a linear scale. When we talk about changing numbers in the Richter scale, we're talking about a 10-fold increase or decrease in seismic wave amplitude and a 30-fold increase in the amount of energy released. So this means that an earthquake with a magnitude of 7 has a seismic wave amplitude 100 times greater than an earthquake with a magnitude of 5, or a magnitude earthquake of 6 is 10 times greater than a magnitude earthquake of 5. This is a very simple example of a seismograph. Here we have a mass, an iron ball or bowling ball if you prefer, with a pen underneath it. And beneath that pen is a rotating paper drum. So this paper turns very slowly. If the Earth is to move in this direction or these directions, then this mass is going to tend to remain stationary while this drum moves beneath it. So this is the inertial object here. It's going to stay in one place. This thing that's attached to the Earth is going to move. We can see examples of this in earthquakes around the world, earthquakes that are occurring right this very second somewhere on Earth. In this particular example, we're looking at the Cypress Viaduct of Interstate 880. This is an outer belt or a ring road around the Oakland, San Francisco Bay Area that comes off of Interstate 80. So this is the October 17th, 1989 Loma Prieta earthquake. And what you can see here is the collapse of the Cypress Viaduct. And two different images here. This is something that many of you, if you're traveling to the American Geophysical Union meeting in San Francisco, it's usually held there every year, not this year, you might get to travel underneath one of these things. And I could tell you, you think about it. When you're in a traffic jam underneath one of these overpasses for, say, an hour or two, you're wondering, when's the next big earthquake going to strike? Now, this collapsed here for a particular reason other than an earthquake. When we take a look at the pathway of the road here, Interstate 880, again coming off of Interstate 80, which is located right here, it runs through this material that is composed of mostly soft mud and some fill. This fill was generated during the 1906 earthquake. So basically we're running a highway across some loose material that is then shaken severely by an earthquake. Here we have a 1-minute video. It's a little longer than a minute. We'll just play a minute of the 1989 Loma Prieta earthquake. Give it a kickstart here. So here at the beginning of the earthquake, we see the release of energy. And you'll notice that there appears to be more energy being released along this band, and this band than surrounding regions. And I'm just going to go out on a limb here and suggest that this is the location of the Zayenta fault. The San Andreas is a little bit to the north here. And I'm guessing there's some rupture occurring along the San Andreas fault associated with the rupture occurring on the Zayenta fault and any subsidiary faults directly associated with that. So you'll see that the energy spreads quickly within a minute. It's essentially off the map here. But it tends to be concentrated right along where the actual rupture occurred. And this is a bit like ripping Velcro apart. So you can start in one spot, and as you keep ripping, you keep expending, in this case, releasing energy by this ripping process.